Today we're going to discuss fossil fuels and their impact on the environment. And the first thing that I want you to know is that we are not talking about ozone. Ozone is a very important environmental topic, but it really has nothing to do with fossil fuels. People often think that when you're talking about fossil fuels, people want to start talking about the ozone layer, and the ozone layer is an important thing. But is completely set aside, different from fossil fuels. So what you first have to understand is that living things, obviously have carbon in them. That's where the fossil fuels come from. But they also have phosphorus and they have nitrogen. Any living thing, a fish or an ant or a platypus or a moss, has all these things in it. And whenever they die and they get turned into fossil fuels, those things are still there. And whenever those things get burned, those nitrogen and phosphoruses, they become oxidized. They go up into the atmosphere as nitrogen oxides and sulfur oxides, and they dissolve in the clouds. So when you add them to water, they make acids like nitric acid and sulfuric acid, and we'll learn about naming acids later, but that's the basic idea, is that these nitrogens, these sulfurs, they get oxidized, they get burned in the plants and in the power plants, and they go up into the atmosphere and they form these acids. So what is acid rain? First thing to understand is the pH scale. You've probably heard of it before. The lower the number on the pH scale, the more acidic it is. And the higher it is, the more basic it is. 7 is neutral, so above 7 is base, below 7 is acid. And if you're really far from it, you're strong, and if you're really close to it, you're weak. So like, as an example, water is 7, but hydrochloric acid, it's a very strong acid, it's around 1. Lye is a really strong base, it's around 13. See, the really strong acids and strong bases are really low and really high, respectively. But some things are in the middle-ish. Orange juice and soda, they're like around 3 or 4. So they're acidic, but they're weak acids. Egg whites are a weak base. Soap is a weak base. And when we talk about all this, we talk about acid rain. Acid rain has a pH, like I said, around 3 or 4. So we're not talking about something that's going to hurt you. It's something like, it's as if it were raining orange juice. When people talk about, oh, don't let the acid rain dissolve you, it's like people aren't really concerned about orange juice dissolving them, and it's the same kind of idea. We're talking about a weak acid. And that's not to minimize things. We'll see what kinds of real effects these weak acids can have on the environment in a moment, but just to get our point straight. Now, normal acid rain is normal rain, not even acid rain, is already acidic due to carbon dioxide. Carbon dioxide, just like nitrogen dioxide and sulfur dioxide, can be dissolved in the atmosphere and make this carbonic acid. Stuff in soft drinks is what gives soft drinks its fizz. But the carbon dioxide in our atmosphere would only give it a pH around 6. It would just barely be acidic at all, and it wouldn't really have any effect. But these stronger acids, these pHs 3 and 4 that you get off of phosphoric and nitric acids. I'm sorry, I said phosphoric. I think I meant... Oh, I didn't. Oh my, I went back. I made a big boo-boo up here. Phosphorus is important, but sulfur is probably even more important. It's actually sulfur oxides that make sulfuric acid. You probably caught that mistake earlier, some of you, but that's okay. Phosphorus also does it, but probably sulfur is the bigger culprit here. So as we go down, so what are the effects? Well, acid rain isn't going to kill you, but it can corrode buildings and statues and make it so that makes it so that some things won't last very well. There's this thing called stone leprosy, and I will bring up some pictures of it. If you look at old statues like that, you can see that they've been corroded through time. Leprosy is an old disease of the skin where body parts would fall off and so it's as though these statues have leprosy. And so you can see it kind of like disfigured, and over long periods of time acid rain can lead to those kinds of issues. And also on buildings, you have a marble facade, it'll lead away at that. The other problem, environmentally speaking, with acid rain is that it can actually change the pH of a lake enough to kill fish by dissolving aluminum. What happens is you have this lake with water in it and fish in it, and they're all happy. But then the aluminum in the soil, what happens when acid rain falls, it dissolves that aluminum and it turns it into aluminum ion in the water. And that aluminum ion is enough to kill the fish. And fish don't care for aluminum. You get too much aluminum in their ponds. And so there are actually cases out west where this has happened, where you have these dead lakes because the aluminum has killed the fish. It doesn't happen so much for us because our soil is basic. We live on top of a big layer of limestone because there used to be an ocean under where we are. So there's like all these shellfish and whatnot left their bodies to turn into our soil that turned a little bit basic. The limestone's basic. It's calcium carbonate. It's basic, and so you can't really dissolve the aluminum in our soil just from a pH 4 or 5 acid rain because there's so much base. Because bases will neutralize acids, and so it can't do that. So what about the other problem with fossil fuels? The second big problem, the one that's in the news all the time, is greenhouse gases. Greenhouse gases trap heat in the atmosphere. So a greenhouse works this way. You have these plants inside. You're like, hey, I'm a plant. I'm going to live. But it's cold outside. And so whenever the sun shines and it's too cold for these plants out here, all outside here, they're all dying. Oh, I'm a dead plant. Oh, no. But as it radiates its heat in, all of the different, the heat, the sun warms the inside of all these different kinds of light, ultraviolet, visible, all these kinds of light get sent into here, warm the place up, and as they kind of radiate back off, the glass ceiling kind of traps the heat, because the infrared heat, it gets trapped by that glass on the top, and so the whole idea is it stays warm inside of there even though it's cold outside, and you don't necessarily even have to have a heater running because it just kind of traps the heat in. That's how a greenhouse works. So greenhouse gas works the same way, except it's on a global basis. So here's the Earth and here's our atmosphere. Certain gases in our atmosphere trap heat, and that's a good thing. So as heat tries to radiate back, oh my goodness, what happened there? That was interesting. So let's try that again. So here's our Earth, here's our atmosphere, and so as heat comes in, it tries to radiate back out in the form of infrared, but certain gases trap it, reflect it back towards the Earth and keep the Earth warm, and that's a good thing because without it we'd be frozen to death. We need those greenhouse gases. But the problem is, if there are too many greenhouse gases, if they're too good at trapping heat, we need some of that heat to filter out into space so we don't overheat. And so there are certain kind of gases that are really good at trapping those. Carbon dioxide and methane are the two biggest ones, because carbon dioxide because it's the most prevalent, there's a lot of it, and methane because, not because there's a lot of it, because it's really, really good at trapping heat. Now methane is natural gas. You've probably heard of carbon dioxide. Natural gas, methane is the same stuff that we burn in our Bunsen burners. It's flammable, and so it's actually one of the fossil fuels that we burn. But also, whenever animals fart or you fart, and a lot of times you've heard maybe studies with people joking about studying cow farts, because and making fun of that, but actually it's kind of important. We need to know how much methane is being released in the atmosphere, because methane is a very, very effective trapper of heat. And so so those are the two biggest gases that we're most concerned about. There are others, but no matter what you burn, burning anything puts carbon dioxide, burning any carbon-based thing puts carbon dioxide into the atmosphere. But natural gas puts less carbon dioxide per unit of heat delivered than either coal or oil, as it says there. There are also less nitrogen and phosphorus and sulfur. Made that mistake earlier. And sulfur. And there are also other heavy metals that contaminate it. A lot of really ugly stuff that you don't want out in the atmosphere is in coal, but not as much as in natural gas. So natural gas is actually the cleanest. Puts less carbon dioxide per unit of heat delivered. There's less nitrogen, less sulfur, less heavy metals. So methane is the best fossil fuel environmentally. Also, the other thing to keep in mind is methane is natural gas. So if you didn't burn methane, it could seep up into the atmosphere and it could act as a greenhouse gas instead. So it's better to burn it and make carbon dioxide. Even though carbon dioxide is a greenhouse gas, it's better to have that in the atmosphere than the methane. And so there are so I don't feel like I said that very well. Coal then is dirty and puts a lot of CO2 into the atmosphere, whereas natural gas is cleaner and puts less CO2 into atmosphere. Also, like I said a minute ago, natural gas itself is a greenhouse gas, so burning it to get rid of it's not a bad idea. Oil-based things would be in between. They're more environmentally sound than coal, but not as good as natural gas. So, environmentally speaking, natural gas is the best of the three. Now, that's not to be confused with saying it's good for the environment. It's an idea of the lesser of evils. Now, why do we really care how hot the Earth gets, you might ask? Well, this is actually a big topic, and a lot of politicians do a lot of fighting about all this kind of stuff. And it is true that there are actually places where it would get colder if the global climate changed. So a lot of people confuse the idea of CO2 buildup with like everything getting hotter, and in general things do get hotter, but there would be places that would get colder. Eastern Europe would get colder, or Western Europe would be colder. So it's really it's a very complex system with all sorts of moving parts, but the basic idea is that the whole global climate would change, and so places that are used to being cold would be warm. Places that might used to but on average everything would get hotter, and more things would melt into the sea, and so the seas would rise a little bit, and that doesn't matter so much if you live in Minnesota, but if you live in a place that's on the beach, it's on the ocean, that could make a big catastrophic change. And so over the last century or so, we actually can tell that we have had some changes. If we look at this this graph, here's a graph that kind of shows over the last since the 1900 or so, last 110 years, you can see this graph of the CO2, like how much CO2 there is the green line there, and the red line is the global temperature average, and so you can kind of see that the two have kind of moved together there. And so we keep burning all this stuff, we keep putting more and more and more and more CO2, it stands to reason that this line would keep going up. And so we need to be thinking about what that's going to do, and we'll have more talk about that later on when I'm in class.